recording also.
This meeting is being recorded.
Thanks. Today's talk is going to be memory consistency models and coherency protocols, which is going to be delivered by Dr. Kalyan. Dr. Venkata Kalyan Tava is an assistant professor in the Department of Computer Science, IIT Ropar. Prior to this, he was a hardware performance architect in the Power Systems Performance team, which is part of India's Systems Development Lab at IBM India. His research interests lie in memory hierarchy exploration, alternate computing techniques, and low power energy efficient designs. He has several publications and patents to his name. Dr. Kalyan received his PhD from IIT Madras. He is also a member of IEEE and ACM. We look forward to your talk, Dr. Kalyan.
Thank you very much, Krish, for the introduction, and also thank you for providing us with such a platform that we can interact with all and share and discuss many of the insights. So I'll quickly share my screen. Please let me know. Host disable participant screen sharing. So Dr. Praveen, I think you need to enable screen sharing for me. You're on mute.
Please check now. Please check now.
Yeah. Yes, I can do it now. Okay. Need to do. Okay. I hope you are all able to see the screen.
Yeah, it is visible.
Okay, thank you. So today's session is going to be on the memory coherency and consistency models. I'm not sure how much of this we can cover in a single session. Because the concepts are dense, so I'll take it slowly, and we'll cover the remaining topics in the coming sessions. So to begin with, okay. So a quick overview of my research interests, just to give my overall profile here. So I primarily worked in DRAM, spanning from performance to power optimizations, then non-volatile memories, again both for performance and power and reliability aspects, then concurrent programming with Dr. Praveen and Professor Madhu on scalability and energy efficiency. A couple of designs where we were able to come up with optimizations where the software would leave hints to the hardware for it to optimize further. Then the cache levels at different levels in the hierarchy, both for performance and power, and hardware security spanning right from cache to the SSDs. And apart from this, another active research is on architectures for graph analytics. So here too, slowly expanding my interest, wherein the application and the architecture are designed in a cohesive manner. So with that, I'll move on to today's topic on the consistency and coherency point. So to begin with, a very general question is how the programmer views the memory, right? From the programmer's point of view, the memory is very simple. It will respond to the data requests. So the data requests are, or we can call the memory operations, are typically reads and writes. Read operation will give the data to the programmer, and the write operation will update the memory with whatever the programmer wants to write to. Now, how does this eventually translate? Is your high-level program would be translated into the assembly instructions, and assembly instructions are typical loads and stores. Load is for read and store is for write. And whenever the memory receives a load request, it responds with data. If it has received a store request, it will update its own content. So that is the simplistic view. And following that, the programmer also can potentially assumes that all the memory operations are atomic, and in the meaning that the memory will handle them one by one, and there cannot be potentially any intervention of one operation when another operation is taking place. The third viewpoint is the order in which these memory operations, these reads and writes, are issued to memory. That is the way the memory would go ahead. Means the first in, first out of this request service is strictly followed, right? And the fourth one is that the memory contents are accessible at a high speed, maybe equivalent to the processor speed. So typically, even in our algorithmic analysis, we always ignore the memory latency, and we so effectively saying that everything happens in instantaneously. So the reads and writes, etc., the updates, and so on and so forth. Right now, to make the programmer's life simple, the architects have worked strenuously over the years, and they have come up with multiple optimizations, starting from just one second. Okay, starting from out of order processing, right? And out of order, okay. It can be the instructions, the way they are getting executed. It need not be the exactly following the program order, but the correctness is ensured by complex mechanisms like Thomas-Hilo, right? And even the memory operations can be processed out of order, meaning that if some memory operation is independent of the operations that have come before it, it can potentially be processed earlier, right? And second is pipelining of both the instructions and memory, right? So this also increases the throughput a lot. And even at the memory stage, even though it's a simple black box for the programmer, there are potentially many small steps that the hardware performs, and pipelining them would help both the latency and the bandwidth, right? And another popular method is caching. And also the cores are now equipped with multi-issue, multi-threading capability, and such cores, multiple of them are part of a single processor, and such a process can be there on a single system, making it a multi-core processor, right? And all these, even if we consider a single application, have a huge impact on the performance, right? Now, let's throw in the multi-threaded programs to this. The complexity increases a lot. How do we ensure that the requests, the memory operations from each of these threads, apparently from the same program, are being responded in that order, right? And the data that is being supplied to the cores that are running these individual threads of the program are working with the correct data, so on and so forth. So this makes the entire design more tricky because of both the expectation from the programmer and many architectural facets that we have in the current complex modern processes. Right now, in addition, even if we consider the simple memory, we said that the memory would respond to the data request primarily by taking an address, whether it is read or write. And what we do also expect is the memory always supplies us with the latest data that is written to that address. Now, even for a single core processor, this might be very trivial in the sense that if we have a let's say we have an array A, and we assign a value of 5 to an element A of 0, right? A of 0 equals to 5. That's what we do. And in following that, we write another instruction on the line in the program saying that A of I equals to A of 0 equals to 5 times A of 0, for example. So what we expect after the second line executes is A of 0 will have 25, 5 times 5. Now, we are inherently making an assumption that line 1 is completely getting executed before line 2, right? And the line 2 is the consumer of line 1, right? And it is expecting the value of A of 0 to be 5, the updated one, the latest value. Now imagine multiple threads working on the same array. It can be on the same array element or different array elements. From the correctness point of view, we need to ensure that all the threads are working with their latest values. And considering the other point about order of the memory request that is being followed, the reads and writes sequence needs to be strictly followed or adhered to, right? In the previous example, we expect the second operation of 5 times A of 0 to happen only after the write to A of 0, right? So even in a single or unicore processor, how does the processor and DMA interact? Makes it interesting in the sense that, let's say the DMA, which is potentially working on its own, of course, based on the trigger from the processor. Let's say it is copying some data from an IO device, let's say an external hard disk or some other place, into the memory, which is currently being used by the processor. Now the processor needs to be informed that it's working with a stale copy. Otherwise, potentially the correctness point will crop up again, right? So even the DMA and the processor need to be handled very carefully. Now, so like I said, how can we in a multi-threaded execution, how can we ensure that the latest value of all the data is being supplied whenever any core asks? Also, how do we ensure that the order of such requests is being maintained, right? That is what we are going to dive into today. So following that, a quick background on how things have progressed. This will help you to understand the many concepts on coherency and consistency as we go, right? And this graph, many of you would have seen quite a number of times, is how the processor speed and memory speed have progressed over the years. There has been increasing disparity between the way how the processor has grown and memory has grown. This has given almost 50% gap every year, right? So, and till 2004-2005 timeline, the memory latency was issue because the memory was not catching up with the processor speed, right? This was the memory wall that all of us are aware. And following that, we have moved from a single core processor to multi-core processor because of multiple issues that Dr. Praveen has mentioned yesterday, primarily driven by the power aspects, for the power density. What happened during this time is, even though the speed of the process, individual process cores was not scaling like earlier, there were multiple cores, and the memory was expected to supply the data for all the cores. So both the latency and memory are of utmost importance now. The performance of the memory heavily depends on how we are able to satisfy these two from the core side. So this is the modern memory wall, right? Our memory, which the programmer assumes to be a simple memory, is no longer scaling well, and more cores are requesting data from it. So with in order to address this serious performance issue, the memory hierarchy was created. So this was the practical way of achieving a very large memory, which is fast, and also which would practically be affordable, right? So, and this entire hierarchy of memories heavily depends on the principle of locality. Like Dr. Praveen has mentioned yesterday, principle of locality has two aspects. One is the spatial locality, another is temporal locality. Spatial locality implies that if a data item is requested by the processor, the nearby data items, locations, you can say, will also be requested. And temporal locality says that there is a high likely chance of reuse of the same data item, right? So the memory hierarchy is typically presented as a pyramid, right, with various levels. As we go from top to the bottom of this pyramid, the latency increases, the capacity of the memory increases, and the cost of the memory decreases. How was this actually realized? Is primarily because of availability of various memory technologies. The top of the pyramid are registers, which can be made with flip-flops, right? The processing technology is same as the processor core itself, so it's quite fast. Following that, we have caches, right? Primarily made with SRAM cells. Following that, we have main memory, which is primarily made built with DRAM technology. Following that, we have the secondary memory, which was earlier built with the magnetic disk or magnetic tape, but now we have flash memory. And here are some sample access times and the cost that these individual technologies would are having, right? SRAM, the access time is in few nanoseconds, and when it comes to the DRAM, it is tens of nanoseconds, so on and so forth. And if you go to the magnetic disk, it is millions of nanoseconds, right? And the cost is almost inversely proportional, saying that the magnetic disks are the cheapest. So if you want to store data, you would typically use a magnetic disk, but if you want to process the data, you would prefer a faster memory like SRAM or DRAM, right? Just like we had flash memory for secondary storage, now we have multiple non-volatile memories. For example, we have STT-MRAM, whose latency is somewhere between SRAM and DRAM. That's the reason it is placed in between them. And then we have a PCM, whose latency is somewhere between the DRAM and flash memory, so on and so forth. So because of these new memory technologies, the memory hierarchy is getting much more deeper. For example, we can have 2 or more levels of the secondary memory itself, where the first level, for the top level in the secondary memory would be the flash which can be ideally called as online storage, and following that we can have the magnetic tape or disk, which can be considered as a offline storage. In the same way, the main memory can be imagined to be in a tied fashion, based on STTM RAM, DRAM on the front end, and with the back, the PCM would be there. Of course, each of these technologies have their limitations also. So the architects have come up with various intelligent designs that help us use these technologies. So, like I said, we have multiple levels. So even at the caches, L1, L2, L3 are quite popular now in almost all the modern processors, right from your high-end mobile phones to the servers, right? And similarly, other main memory and secondary memory, right? So whatever I've spoken and said, like, this is quite followed in the modern multi-core process. So here is the snapshot of a 4-core process. We have 4 cores. And following that, we have L2 caches, which are co-located with each core. And so the L1 caches are part of the core itself, right? They are sitting right inside the core, and L2 is sitting beside the core. And following that, we have a huge shared L3 cache. The shared L3 cache, meaning all the cores can access it. So the L2, which is co-located with core 0, for example, cannot be accessed by other cores. So we call such levels as private caches, and the others as shared caches. Following the shared L3 cache, we have the DRAM, right? And DRAM is primarily paired with DRAM banks. I'll not dwell deeper. So it is controlled by a DRAM memory controller. Following the DRAM, we have the storage, online and offline, based on SSDs and magnetic disks, right? Now, like I mentioned, L1 instruction and L1 data cache are part of the core itself, and the registers, as you are all aware, are sitting right beside the pipeline itself. So a block level representation of what we have discussed so far. At the top, we have the register file, and typically the size of the register file is quite limited because of the speed at which it is expected to work. So typically we'll have 64 or 128 registers. Some advanced processors can have a little more, but nothing beyond that. And following the registers, we have the L1 cache, and the data transfer between the register file and the L1 cache is done manually, meaning either the programmer or the compiler will instigate this, right? And if the data is being moved to and forth the register file a lot, we call that register spilling. From L1 to we follow to L2, right? Then we have an L3, right? The data transfer between these levels, L1, L2, and L3, is automatically done by the hardware, meaning the programmer or the operating system has no role in the data movement, right? And following that, we have the main memory, and then the secondary disk, right? The movement of data from the main memory and secondary memory is done by the operating system, right? Now, this is the memory abstraction that we were earlier talking about, right? Each level, the data movement or how that level works is abstracted out from the levels above and below intelligently, right? Now, we will focus on the cache memory a little in detail, and I'm going to take some specific points from here to connect to our current topic, right? So it's based on static RAM, right? And each cell, we can, in interest of time, we can ignore this. Each cell stores just one bit of information. It can be either a 0 or a 1, right? It is called static because it does not need refresh, meaning that if you store a 0, it will continue to be 0 as long as it is powered on, right? And it is volatile in nature. It means that whenever there is uh, uh, power loss, all the data will be lost. Then, as you know, multiple levels of cache are common, but all of them are primarily made with SRAM technology, right? And the working of all these caches, the actual hardware, is more or less same, right? So we have the core. Following that, we have the L1 cache. The core gives an address to the L1 cache. Consider a read operation is happening, right? And the L1 cache will supply the data to the core, right? Now, if the L1 does not have the data, which we typically term as a mess, the request is forwarded to the next level, which is L2. And if L2 has the data, it can it will send the data to L1. Also, in parallel, it can forward the data to the core to speed up the processing. If L2 also does not have data, the request is forwarded to L3, so on and so forth. And eventually we'll go to the main memory. And if we see that the main memory also does not have the requested data, we would call that as a page fault. And we need to bring in the new page in its entirety, and the OS gets involved there. Right now, if we observe the granularity of accesses, right, between the main memory and L3, it is only a block of data. L2 and L3 also block of data. L2 and L1 is also block of data. But L1 and L2, L1 and core is a word of data. A word is a smaller chunk, can be 2 bytes or 4 bytes or 8 bytes, and a cache block can be typically of 32 bytes or 64 bytes, right? So the immediate question that can crop up to our mind is, why are we sending a block of data instead of a single word that the processor is requesting? So the answer is, again, to exploit the spatial locality, saying that maybe the adjacent words can be potentially reused by the or used by the processor, right? Now, the cache can be viewed as a collection of blocks, and like I said, each block is a set of words, and the overall cache size that we typically talk about is arrived from the number of blocks and the size of each block, right? So as an example, I've mentioned a 32 kilobyte cache, which can be made up of 512 64 byte blocks or 1024 32 byte blocks. So it's simple math. Now, the way we can imagine a typical cache is that all the blocks B0, B1, B2, etc. are arranged in such a sequence, right? And each block will have individual words, word 0, word 1, etc. right here. And each word is made up of individual bytes. Here I mentioned B0, B1, so on and so forth, right? So when we say the memory is byte addressable, right, in general, all the systems are byte addressable. Each of these bytes has a unique address. Now we are abstracting that at the word level when we are coming out of the processor. Then we are abstracting that to the block level when we talk about the caches, and we are abstracting that to a page when we are talking about the main memory, primarily to exploit locality, right? So let's say the address of this particular block is 1000, and the next block is 3BEF, all in hexadecimal, so on and so forth, right? Right, this way we have filled the cache, and the 1000H is the address of the first byte of this whole block, right? That is important to note. And this particular data is already residing in the main memory, and a copy of it is brought into the cache to be worked with. It can be, all the cache levels potentially, right? And we call the set of blocks which are actually storing the data as the data array, and the ones which are storing the address as tag array. Right now, how does the cache work? We have a sequence of or a collection of blocks along with their addresses. Now, the processor can send an address to the cache, then there will be a control circuitry which is called cache controller, will take the address, and now it has the job of it is to take this address, go to the corresponding entry in the cache, and take the particular word and give it to the processor. Now, how does that happen? Right. So from the address it gets, it takes a part of it, which is called a part of it, and compare it with the tag array. Right. If there is a match of this address, then then the data that is requested by the processor is actually present in the cache, and we call this as a cache hit. Right. On cache hit, like I mentioned earlier, the data, a copy of the data will be sent to the processor. If there is no address match, then we call it a cache miss, and the address is forwarded to the next level of the hierarchy. Now, even though this looks very simple, primarily to understand a little finer in detail, we'll take 4 questions on how the typical cache would work. Right. So where can a block be placed as question 1? It's the decision or the choice that we have is called block placement. How is a block found is called block identification. On which block can we replace on MS? Because the cache is smaller than typical size of a program, eventually it gets filled up, and we need to kick out some existing blocks to make space for the new blocks. So how do we effectively pick this block that needs to be evicted? That's called block replacement. And the 4th one is what happens on a write. What happens when the cache receives a write request from the processor? So this is termed as write strategy. So I'll quickly walk through these 4 questions to understand the working of cache in its entirety. Right. When it comes to block placement, where can I place the block? Right. I can potentially say that the block can be placed in anywhere in the cache. It's called a fully associative cache. If it is on the contrary, if I can place it only at one specified location, it's called direct mapped. If it is somewhere between that, a few set of locations can be used, it's called a set associative cache. Right. And if there are n possible places where the block can be placed, it is called n-way set associative cache. So let's quickly understand this with example. We have the main memory. Let's say it is now we are using block numbers to identify individual blocks, block 0, 1, 2, etc. So let's say our memory has 32 locations. Right. Now, if it is a fully associative cache, then okay, let me opt. Let's say the processor has requested block number 13. Now, if I can place block 13 anywhere in the cache, so here I have considered a cache of size 8 blocks, right? Whether it is fully associative or direct mapped or 2-way set associative, right? And in the first case, we are considering a fully associative cache. If I can potentially place this block anywhere in these 8 locations, this would be a fully associative cache. In direct mapped cache, there will be only one specific location where I can place this data in a. And how do I find this location is primarily by dividing the block number or the block address with the total number of blocks that can be stored in this cache. So here it would be 13 upon 8, and the remainder is 5. So I would be placing it in the 5th location. If it is two-way set associative cache, then in a similar fashion, I would pick the find out the 2 locations that I can place in. So this is called a set. So a group of these 2 locations is called a set for a two-way set associative cache. And if we talk about direct mapped, each of these locations is a set. And if we talk about fully associative cache, then all the locations together form our set. Right now, let's say we have picked the fully associative cache. We have the possible designs: fully associative, direct mapped, and set associative. Now, when the processor is given as an address, how do we exactly find where this block is? So we will be looking at the address. So the processor has given us some address, and we divide that. We, meaning the cache controller, divides that into block offset, index, and tag. Right. So the tag and index together will form our block address. Right. And within the block offset is a unique location for each of the bytes in that block. Right. And the width of each fields can be identified by looking at the size of individual cache block in the overall cache size. Right. So let's say our overall address is 40 bits. Right. And let's say that our cache block is of 16 bytes size. So block offset would be the LSB 4 bits, 0, 1, 2, 3. Now, if we consider our cache size to be 128 bytes, then the number of blocks would be 8. So effectively, I can fit 8 blocks of 16 bytes each. That's what it would mean. Now let's consider how it will look for each of the 3 design choices that we have: direct map, set associative, and fully associative. For direct mapped, we will have 8 sets. Right. And how did I get 8? Is by dividing. So in a direct map, each block will have its own dedicated set. So because the number of blocks are 8, we have 8 sets. Right. Now I need 3 index bits to identify each of these sets. So the total number of index bits is 3, and the remaining 33 bits would be the tag. So these 33 bits of tag will be stored or co-located along with the actual data. Right. And the index bits would be 6th, 5th, and 4th bits of the address. And remaining would be the tag. The same way, if we take a two-way set associative cache, we will have 4 sets now, and each set will have 2 blocks because it's a two-way. So the index bits that would be required to identify one of these 4 sets would be only 2 bits, and the remaining would be tags. In a fully associative cache, because all of them belong to one set, the index bits, there are no index bits, and potentially all of them will be treated as tag bits. Right. Now, if it's important to understand that we not only store the data, we also store part of the address of this data. Now, so in interest of time, I'll quickly walk through what happens in a direct mapped cache. Right. If we consider a cache of size 2 power k blocks, then there will be 2 power k sets. So we need k bits as index. We use that k bits extracted from the address that came from the processor. We use that to go to that particular set in the tag array. We read out the tag array bits, those the k bits that are stored in the tag. We match that with the requested addresses tag. Right. If those match, then we would call it a hit, and accordingly we will pick the data from the data that we read from this set. Okay. And if it is a hit, then the specific word that was requested or the specific byte that was requested can be identified using the block offset, right? In the similar way, we extend that in in a two-dimensional fashion. Instead of one array, we have two arrays in the data array and tag array, right? Way 0 and way 1. And what follows is something similar with the direct map, just that the index bits are now k-1 instead of k. Two tag entries and two data entries would be read out, right? And whatever has been read out, the tag entries will be matched with the requested ones, right? And we'll identify a hit or miss based on the match. Okay, in a fully associative cache, because there is only one set, we effectively need to compare the incoming address, the tag of the incoming address with all the blocks. And if there is a match, then we would call it a hit, but effectively we are comparing all the blocks tags, so it's not energy efficient here, right? So each of these design choices, the direct map, set associative and fully associative, have their own pros and cons, right? For example, like I said, fully associative cache will consume more power, but it effectively shows high hit rate, and hit rate would eventually translate into performance, right? So I'll pause here for a moment. Are there any questions till now? Okay, so let's go ahead with okay. Yeah. So with respect to block replacement, this is not directly related to our topic, but I'll touch it a bit for completeness sake, is which block to replace if the particular set is full, right? And what triggers this block replacement primarily is a cache miss. So we got an address from the processor requesting data, and we compared it with the cache, and it was a miss. And we also realized that the entire set is full, so we need to make space for the new block, which has been the request for which has been forwarded to the next level of cache. So one of the existing blocks need to be evicted, so we call that as a victim block, right? How do we pick the victim block? Is following a replacement policy. Now the replacement policy can be quickly for direct map, it is straightforward because there is only one block per set. We need to compulsorily evict that block to make space for the new one, right? For the set associative and fully associative caches, because there are multiple candidates, we need to pick one of them. So we can go with either random policy or LRU, least recently used, or FIFO, so on and so forth. Now, how do we identify that some particular block is least recently used, or it has come first? So all this information needs to be additionally stored along with the cache block and tag, right? So this we call the recency information. So along with the cache block, we are not only storing tag, we are also storing the recency information, which will help us for the replacement of the blocks. The last question is write strategy, is how the cache will handle a write. Now, how are writes different from reads? So there are a few points. To begin with, the number of writes are very, very less compared to reads. So on top of it, instruction cache will primarily have only reads. Of course, there are some exceptions in modern process, right? In the data cache, the common observation is that there are at least 2 times reads when compared to the writes, right? So most of the cache designs are optimized for reads. So this is called a design for common case. right? It is one of the architectural ideas that is followed at all levels of the design. Now, the other point is writes are not primarily on the critical path, right? Meaning that the processor does not stall on writes, it stalls on reads, means it is the instruction that is waiting for the read is the consumer, and typically a write is the producer. Sorry, write is not a producer, rather it never, excuse me. So in a uniprocessor environment, the processor never typically waits for the writes. Okay. Yeah. And also the write buffer can be used. For example, we have the memory access stage in the pipeline. It sends an address to the data cache, and data cache supplies data to it if it is a read operation. But if it is a write operation, when the memory access stage, of course, if there is a load, store, queue, etc. in between, right? Along with the address, the data is also sent, right? It can be potentially placed in a small buffer. Like I said, the load, store, queue can potentially be used, wherein both the address and data can be stored, right? So on and so forth. And whenever the data cache is free, the writes can be done. From the processor point of view, the write is done, right? So it, like I said, first thing is it doesn't wait on writes. Second is the number of writes are less. Even on top of that, if we, from the processor point of view, the write is done, right? So for reads, tag and data accesses can happen in parallel, but for writes, we can modify the block only after the tag match. So the writes are slower when compared to reads in a typical cache access. And accordingly, we have some pros or some benefits and some shortcomings with writes. And the design choices we have for writes is different when compared to reads, right? So that's where we have the write policies. The first choice is write through, second is write back, right? And the second design choice that we can have is write allocate, or no write allocate. Or so let's try to understand what these are, right? The write allocation policies will come into picture only when the requested data memory operation is a store and it resulted in a miss. So simply write miss operation, right? So in a write back cache, whenever there is a write from the processor, it will be updated in the block, in the cache, in that corresponding block, right? And the next level of the memory hierarchy will not be updated immediately. Only when the, let's say, we have two levels of cache, L1 and L2, and the processor has issued a store, executed a store instruction, the data will be updated in L1 only. If it is L1, write back cache, right? And the updated data will not be seen by L2. Only when this particular block gets evicted from L1, it will be updated at L2. This is a write back operation or write back cache, right? It doesn't allow the lower levels of hierarchy to see the writes, basically. Now, in such case, how does L1 identify at the time of action? It needs to clearly say that this is a modified block or not. So we have another status information, which we call dirty bit. So if the dirty bit is set, if the dirty bit is set to 1, it means that the data of that corresponding address has been modified. So whenever this block gets evicted, if the dirty bit is set to 1, it will be updated in L2 also. Otherwise, there need not be update at L2. Right. The pros are that writes are handled within this level. So, and they are fast, and it is power friendly also. It means that unnecessarily all the lower levels of cache need not be updated, right? And the upper levels of cache will absorb as many writes as possible before the block gets evicted. So this will result in less bandwidth usage, right? Now, the other choice we had was write through cache. Write through cache, unlike write back cache, what it does is whenever it sees a write request, it will perform the write. It will update the data in its own cache and also forwards the request to the lower level of cache. Right. So if we have L1 and L2 and L1 is write through, if it has seen a write, if it has received a write request from the processor, it will update its data and also forward the excuse me, that write request to L2. So L1 and L2 will always be in sync in that sense, right? It is easier to implement than write back cache. And the cache is always clean. It means that there is no dirty a block in the cache itself, right? In a write back cache, when there is a read miss, then it can potentially generate another write request if the victim block is dirty block. But in write through cache, that will not be the case. So handling a read miss can be slightly easier in case of write through cache. And given that the next level of memory is always updated, write through helps to maintain data coherency, right? But the biggest disadvantage with write through is higher utilization of bandwidth and power, because lower levels of memory will also see all the writes that are happening, right? Coming to the write allocate policies, when there is a write miss, meaning the processor has sent the data and address, and it wants the memory to be updated with that new data, and we realize that that particular block is not there in the cache. Now the choice we have is bring that block from the lower levels of memory and update, or yes, Dr. Praveen, can you unmute Okay, I think I am able to mute. So
Okay.
Yeah. So when there is a write miss, so the decision we have is whether we need to get this block from the lower level of cache, allocate a place in our level, or we can directly forward this request to the lower level and tell it to handle. So whether we are allocating the space to this incoming request or not is the question. So if we are allocating, it's called write allocate cache. If we are not, it's called write no allocate, right? It's as simple as that. So the main aspect with write allocate cache is the process the cache controller will follow. The steps it will follow will be similar for a read miss and a write miss. But on no write allocate, because it directly forwards the request to the lower level of cache, it will not do anything, and the contents of the cache will not change at that moment, right? So this would be no write allocate would be a preferable choice if the data that is written will not be reused in future. right? So an example is consider a fully associative cache, a write back cache with many entries, and assume that it is initially empty. Now, let's say the sequence of accesses that this cache is observing is write to a location 100, followed by another write, then read to a location 200, and write to a location 200, and write to a location 100. Now, if this is a write back cache, right? So we are not going to kick out a block unless it is a victim block, right? Now, let's try to understand the impact of the write allocate and no write allocate on the overall working of the cache, right? So when write 100 is observed, right? Write allocate cache initially, because it is empty, it will experience a miss. It will bring in this particular location, the block with location 100, and write it into its cache, right? No write allocate also has seen a miss, but it will just forward this request to the lower level of cache. The next time we get this an update for the same location, the cache with write allocate policy will experience a hit, and no write allocate will continue experiencing a miss. And if there is a request for a new location 200 and it's a read request, both of them will experience a miss. And in this case, both the caches will bring this location, this data, and write it to themselves, right? It is ready. Now, when write to the same location is received, both the caches will experience a hit. And following that, let's say we have another write request to location 100. The write allocate cache will experience hit, and no write allocate will experience a miss. So if you see, the total number of cache hits experienced by a write allocate cache are higher in this case when compared to no write allocate, primarily because the data reuse is happening. If there is no data reuse, then potentially the write allocate cache can lead to more misses, because we are unnecessarily allotting place to these blocks. But we don't have a priori that they will not be reused. So it's a tricky decision to make. So a cache design with any of these possible combinations is can be seen. And we can have a write back cache with write allocate policy, write back cache with no write allocate, write through with write allocate, and write through with no write allocate. So normally we would go for design 1 or 4, wherein we go with write back cache with write allocate, or write through cache with no write allocate. Our choice 3 is not of much use, because all the writes are seen to the lower level anyway. So there is no need to give the place, as place in this level of cache for write misses, right? So it can just it is of no additional use. Of course, it can still hurt the performance. So choice 1 is typically preferred over choice 2, in the hope that there will be multiple writes to the same block, right? And in a typical multi-level cache hierarchy, each cache can have its own design, meaning that L1 can be a write back cache and L2 can be a write through cache, and L1 can be write allocate, L2 can be write no allocate, etc. Now the point is here saying that whether the writes are visible to the next level or not, right? So after this takeaway slide, I'm going to break for 5 minutes as requested by Dr. Praveen, right? The cache controller will respond to the request from the processor. It extracts tag, index, and block offset, and according to the cache design, it will go ahead and extract the data. It checks for hit or miss, right? And it generates a new request to the below levels or the interconnect that is connecting to the below levels. It can be typically a bus, right? Each cache block contains not only the data, but part of the address, which we call tag. Along with that, we have a lot of status bits like the dirty bit, valid bit, recency bit, etc. Now, we also have seen that write back caches are possible, write to caches are possible, and write allocate and no allocate caches are also feasible. I'll pause now. We'll carry forward these observations and move on to the coherency of memory. So in the meantime, if you have any questions, please ask. Thank you.
Kalyan, do you have a question here?
Okay, question is, can I use Morris Mano for these concepts? Wasim, I would suggest Computer Organization and Design by Hennessy Patterson for this, right? That's a better book because it explains concepts at architecture level a little more in detail, right? It doesn't go into the device levels, but it at architecture level, this would be good. Okay, any other questions?
Please unmute yourself.
Yeah, thanks, Dr. Praveen. I actually forgot that I was on mute. So, question from Karthik is, what if my cache is not set associative? So can you please elaborate a little more, Karthik? So in the meantime, I'll answer Amit's question, right? Computer organization and design by or you can go for computer architecture. So either of these books would do. So Karthik, can you please elaborate your question? Karthik? I meant to ask, what if my cache is designed in a way that there are fixed mappings? Okay, fixed mapping. So if you can speak, it would help. I know it can, make it easier for you.
Hi. Yeah. So you can hear me, right?
Yes, correct.
Yeah. So I mean to ask, I was probably not there for the initial part of the session, but does the type of cache being used here affect this significantly? I mean,
Effect. Um,
no, my concurrent, the entire methodology, is that affected by the type of cache that's being used? What if I use a direct map cache, something like that?
yeah. So the design choice about whether it is direct mapped or set associative or no fully associative will not have impact, but the choice about whether it is write back or write through or write allocate, write no allocate will have an impact. So to emphasize those points, I covered right from the beginning. I hope I answered your question.
Yeah.
You suggest some recent tools for low level programming. Low level, I am assuming you want to work at assembly level. I would say for RISC-V, I say, right, you can use Venus simulator, right? It would it would help you understand how the assembly execution at the assembly level would work. Of course, it will also help you understand how to write an assembly code, right, and how to deal with registers, the data movement between the registers and the memory, etc. So I hope I was able to answer your question. Okay. Okay, Dr. Praveen, shall we go ahead?
Yeah, please go ahead.
Okay. Okay. Can we have a sample code which has all concepts? Sample codes, I didn't get your question. This is from KBK Rao. Okay, so there are cache simulators that will help you understand the impact of this direct mapping or set associative, fully associative mappings on the cache performance. Okay, and so I think we can share those details for you to a little more play around a little more to understand this, right? There are multiple simulators in that context. We'll share it. Okay, so whatever we have seen so far is that okay. That there are multiple levels of caches, or the overall there's a hierarchy of memories that can be there are at an abstract level we can view it as something like this. We have multiple we can have multiple processes. They are all sharing a single level of cache, right? There is no private cache, etc., right? And the all these are connected via a switch, and if there is a miss in the L1 cache, we would go to the main memory again. All these process are able to see the main memory as a single unit, right? Or the one which we commonly have is where the process have some dedicated cache levels. Following that, we have an interconnect like a simple interconnect like bus, which is connected to the main memory and a few set of IO devices, right? Or if we further extend, we instead of a simple bus, we can have an interconnection network, can be a mesh or torus or a butterfly network, etc. Right? It's again a design choice, and we have multiple memory modules here. Right? Here there is a single memory. And one other approach, it's called distributed memory setup, wherein each processor can have dedicated private cache, private memory, right, or co-located memory, let's call it that way, connected over an interconnection network. So here the distributed memory can be imagined to be, you can have processing nodes, right? They are all connected over then, or the Ethernet or something like that, right? So, but they're still trying to communicate with each other. So, OpenMP kind of libraries will help you to work in this setup, right? So today we are going to primarily focus on shared memory, not distributed memory. So, what actually is cache coherency problem that we want to look at, right? So let's say we have three processors, P1, P2, 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 P3, right? And they all are connected. They all have a private cache, right? Connected to a single memory unit over a bus, right? Now these numbers in circles are the individual steps. Let's say at the very first, the processor 1 has requested for a data item u, right, which is having the current value 5. So the memory will supply this value to the cache, and cache will eventually supply it to the processor, right? So following that, let's say we have another request for the same data location u, right, by P3, right, and it takes the value of 5 and it has processed, and let's say it has generated a new value of 7. So a write request from P3 has come to its dedicated cache, the private cache. So internally the value of u has been changed to 7, right? So all these cores or let's say processes, right, are executing, are part of the same parallel program. Now, if a P1 wants to continue working with u, it should ideally work with this updated value, which is 7. But if it continues working with 5, that would lead to potentially wrong results, right? Also, at later point of time, if P2 has requested the same data item u, right, the memory is also having the stale value of 5. So this is the coherency problem, and in this setup we would say that the caches and memory are not in sync, or they are not coherent, right? So what is actually happening is the if there is a value update by one of the cores, it is not being reflected to the other cores or the memory, right? So such a setup, would it change for the write back caches? So whatever we discussed is primarily, you can say, for the write back cache, for example, right? So until and unless the block in the private cache of P3 is kicked out, the memory will not get updated, right, for write back caches. But still P1 and P1 will be out of sync, and P2, if it has requested if P2 has requested the block after P3 has kicked out the block, right? Only then it will have the updated value of 7. Otherwise, it might, if it has requested before, it can still keep working with 5, right? This is for typical write back cache. But what about write through? Will it solve the problem? So if whenever so consider a case that all these private caches are write through caches. Now when P3 has updated the value of u from 5 to 7, right, because this cache is write through, this will be sent to the memory also. So the memory will get updated right at that moment, but will the private caches of P1 and P2 get updated? So what do you think? Will P1 and P2 get updated even if they are write through? Need not be, right? Because there is no explicit mechanism for them to react on the writes of other process, right? So that's what we need to now include, that piece of logic. So which we commonly call as coherency protocol, but we are going to we'll go to that eventually, right? So a formal definition of cache coherence. So forgive me for too much of words in the slide. I wanted to give the exact definition here, right? A memory system is said to be coherent, right, if any execution of a program for each location, right, we can recreate a hypothetically serial order which is correct, right? That will help us understand how the data has been updated across all the participants, right? So meaning that operations issued by any particular processor will occur in the sequence that was issued by them, right? If it has a write followed by a read followed by another write, etc., that will keep continuing with respect to that processor, and the value returned by each read operation is the value returned by the last write to that location in the above sequence. Now what does this mean is in the previous case, when P2 has requested, it should see a value of 7, not 5. That's what coherency means, right? And the first point number 1 says whenever P3 has updated the value of u from 5 to 7, P1 also should see that the value has been updated. Now whether it needs whether it has the actual updated value or not is another question, but it should be aware that yes, the value of u has been updated and the value it has in the cache is stale. So under these circumstances, we would say that it is a coherent system, right? So whatever I said is called write propagation, means writes become visible to other process or cores for simplicity. Write serialization, it means that all writes to a location from the same core or different cores are seen in the same order by all the cores. Meaning, let's say if P1 has written to u the location first and then P3 has written, even P2 needs to observe that the updates have happened in sequence like P1 followed by P3. Okay, so these two are important to maintain coherence. Now the bus-based setup that we have taken helps quite a bit for coherency, right? Because all the devices are connected to the same bus, they can potentially observe the activity of the bus. If some particular block has been requested or updated, etc., all the other parties can observe that and react to it. Now that's what we need to include. So for example, in the previous example, let's say this is P3, it has updated the value of u, right? And in the write back, in the write through cache, right? So this cache will immediately issue a write request to the memory. and because P1 is on P1 and its private cache are also connected to the same bus, they can observe that yes, P3 has been updating some value because both the address and data will be placed on the bus. The private cache, specifically its cache controller, can latch onto this address, see if its address is there. It can choose either to update the data or maybe invalidate the data. So there comes the again design choice on update based protocols or invalidation based protocols. Okay. Now the cache controller will snoop the bus and will act accordingly if the data, if the address is pertaining to it. It means that it will go whenever an address is placed on the bus, the individual cache controllers will go and will latch onto that address, check if the address is a hit in their caches, then they will have to act on what specifically would there be action items. That is dependent on the exact precise policy that we are going to look at, right? Now, okay, I see a question here. At what point of time will a cache controller do bus snooping? Always on writes? Yes, on writes and also on reads. It needs to do some activity on its front. We are going to look at those actions as we go, right? The key properties of this snooping-based coherence is that all the transactions are visible or placed on the bus and are visible to all the cache controllers, and the cache and the order in which these transactions appear will be same across all the cache controllers. So this, like I said, it solves many problems with cache coherency, and this is one of the reasons that the order is maintained. So here, again, the design choice of whether we went ahead with write-through caches or write-back caches will come into the picture. So if we have write-through caches, then we have coherence protocols which are based on update, right? What it means is when, let's say this Pn has written some value and P1 has observed that that particular block is already sitting in its cache, it will update the value with the newest value, meaning that let's say the value of u was written updated to be 7, right? So it will update its own private cache with 7. Anyways, memory will get updated with write-through caches, right? Now with write-back caches, what should happen ideally is the processor, if it finds that the value has been updated, it will go and mark. You remember the tag, status bits along with the tag that we store. One of them was the valid bit, right? So it will go and make it invalid. So that is why these are called invalidation-based protocols, right? So in the update-based protocols, if I have the address or if I have the block already sitting with me being the cache controller, right? I will update it. If it is write back caches, right, I'm going to check the cache and say that okay, this particular value has been updated, so whatever I have is still, accordingly I'll mark that particular block as invalid. Now because even the let's say here the Pn, the cache is also write back, it will not put the updated value on the bus, but rather it will say that so and so address has been updated. So even the memory will mark itself as invalid. Okay, so next time when some other processor requests for data, now it is the onus lies on this particular processor to supply the data to it. Okay, so this is how the bus will be snooped even for read requests, and some actions need to be taken. So in general, a snooping-based protocol ensures that all the transactions appear on the bus and each cache or the cache controller monitors these and takes the suitable actions. There's a question from so if it is anyway going to be writing to memory, wouldn't it write the value itself? So like I said, it's a write back cache. It will be updated only when the block gets kicked out of the cache, right? So it will be updated, just that it not immediately. I hope I answered your question, right? So the two architectural components that are heavily used in Snooping-based coherence are the bus, basically the transactions that are placed on the bus. They are the trigger points, right? And the cache controllers will take actions based on these transactions. So each cache block can be imagined to be having a FSM, right, which will change the states, right? Now we are going to walk through some of those, right? So the Snoopy protocol is a distributed algorithm represented by a collection of cooperating finite state machines. So each of the cache block can be imagined to be having an FSM, right? Meaning that, let's say in the previous example, when U was updated to 7, and we are following with the write back, we are going with the write back caches where invalidation is happening. So P3 says that so and so address has been updated on my friend, please invalidate yourself. By looking at this transaction on the bus, P1 and P2 will latch onto the address, say that, oh, okay, I have the copy of it, I will go ahead and invalidate. So the block, if it is residing in both P1 and P2, right, it will be in the invalid state. So that's what it means that means by cooperating finite state machines. And in P3, it will be in some other state based on the protocol that we are going to follow. So we are going to look at some more details, right? So each cache block has a set of states, right? And these are specific to the local caches, right? And based on the transaction placed on the bus, these the states would be changing, right? How they are changing is the actual protocol. So, and these the actual actions, like I said, are form the core of the protocol. They are heavily dependent on the design choices of the bus or the cache, like and like write back, write through, write allocate, write no allocate, so on and so forth, and others, right? So now, like I said, each private cache has blocks, and each block has a specific finite state machine. They all work collectively, right? It doesn't it should be the case that P2 will go ahead and update its value, the valid bit to be 1, and P1 will update it to be 0, making it invalid. So it never happens that way, right? The cache controllers will be the action items taken by the cache controllers are specifically designed, and they have to follow it. Now, a simple example on considering a write through cache, but we are going with write no allocate policy, right? So each cache block will have two distinct states. One is valid state and the other is invalid state. Now I just need one bit of information per block to identify these states, right? Now if now let's carefully walk through this state diagram, right? So it has it has few arrows. The solid arrow is the request that the cache got or the cache controller received from the processor, and the dotted line is the transaction that it has seen on the bus. Okay, that's how we understand these arrows. And on top of each arrow we have something written, right? X upon Y, let's call it. This X is the trigger and Y is the action it has taken along with some state change. Okay, so let me walk through this. Let's say we have the cache is initially empty, so all the blocks are invalid. Now the processor has sent a write request to us. That's what PRWR would mean, processor write. Now what will happen, because we are going with a write no allocate cache, the block will continue to be in invalid state, meaning effectively that the block is not there in the cache, and we are not we decided not to allocate the space anyways. So what it will do, the cache controller, is it will issue a write transaction on the bus. So that's what it means, bus write. So upon seeing a processor write and realizing that the block is in invalid state, the cache controller says that I am placing the write request on the bus so that the lower levels of memory can update themselves. Okay. Now, if in invalid state, if the cache controller has received a processor read request, because it's in invalid state, it means that it's a cache miss. Because it's a read miss, it has placed a request on the bus saying that, boss, give me this data. So the lower level of cache will fetch the data for it and respond to it. And when the data comes back, this block will be placed in the valid state. Okay, now we are in the valid state, and as long as the processor read requests are arriving, it means that there are continuous reads to the same block. They are all practically cache hits. There is no explicit action item on the bus, so that's why we have placed dash there. If there is a processor write, and because we went ahead with write through cache, all the writes will need to be reflected to the next level also. So upon receiving a processor write, and if it is a cache hit, this cache controller will update the cache, and also it will place this write request on the bus. Okay, now when so these are all with the solid arrows where the processor has been requesting us. Now there can be potential requests from the bus or from the bus end also, meaning that some other cache is requesting for the data, or the memory is requesting for the data, right? So I have the block in valid state, and the cache controller has seen that there is a bus write request. This bus write request would have been placed by some other cache controller. It doesn't react because it's a write through cache, and it is not going to allocate even if it is a miss, right? I would say take a moment, try to understand this small example, so that we can move on to a little more complex examples. Try to understand the state diagram and shoot any questions if you have. Okay, we have one question. Why don't we have any bus read arrows which are bus snooper initiated? So here in this case, the lower levels of memory are anyways having the updated value. So if I am in I state, meaning that the cache block is anyways a cache miss, and I will not allocate any place for it until the processor has requested. So I will still remain in the I state. If I am in valid state, because the processor has already the next level of memory is anyways having the updated value, I need not react on a bus read. So it's a valid point that that arrow is missing, but I hope I was able to explain what would potentially happen. On a bus read, nothing would change here. If I'm in valid state, I'll continue to be in valid state. If I'm in invalid state, I'll continue to be in invalid state. Okay. That's a good catch. The diagram needs to be updated. Okay, any other question? Okay, let's move on then. So at any given point of time, if things are not clear, please shoot a question. So from this simple two state where we had the valid and invalid thing, right? So let's build our very first three state policy, which is invalidation based, meaning that I have used write back caches, right? Talking to each other with their memory. So for all these examples, the textbook way is to deal assuming that there is only one level of private cache. So, but you can question what about multiple levels of cache at each processor, right? So the last level of cache, which is interacting with the bus, will take up this responsibility. Okay, that's the way we can visualize it if we have multiple levels. Now, in this three-state protocol based on invalidation, right? We have three states, which is modified, or we can call it a dirty state, wherein the data of the block has can potentially be in a modified state or updated state. Then there is an explicit state, which is shared. And the third one is an invalid state that we have already seen, whether the block is there and it's stale, or the block itself is not there, right? So its state diagram would look something like this, right? Again, the same for another. Solid arrows are triggered by the processor, and the dashed arrows are triggered by the bus. And the cache controller is actually observing the current state of the block, the the trigger point, and accordingly it needs to take an action. Now let's try to understand it, right? So, okay, how do I? Okay, this Zoom thing. Okay, now we are in invalid state, meaning that the block is present but stale, or block itself is not present. And the processor has requested for the block, and with using a write request. So we are, if by looking at this state diagram, we can say that we are going for a write allocate policy, right? Otherwise, we would continue to be in invalid state and just say, put a bus write in to the lower level, right? So we can figure out by looking at the protocol saying that it is a write allocate cache, right? So it has received a write request from the processor. So instead of a simple bus read and bus write, now we have a new command on the bus, which is bus readx. Readx meaning read exclusive, means the this particular block is being requested by the processor so that it can be modified. So that is the reason we are asking for exclusive rights, so that we'll have complete ownership of this block. So when the bus read this bus readx is seen on the bus, the other cache controllers will react accordingly. We'll come to that. Now this cache controller, which has received the bus processor write, will place the request on the bus saying that I need this block with exclusive rights, and it will move this block from invalid to modified state. Because the processor is the moment the block comes to the cache, because we are following write allocate policy, the block comes to the cache, we'll update it with the data given by the processor. Okay, now in the invalid state, coming back to the invalid state, if the processor has requested for read, so we will place a simple bus read like earlier, and we will move to a state called shared state. Now, what shared state means is the processor has a valid copy of the data, but it doesn't have permission to write to it because the block is in shared status. It potentially means that some other cache also, private cache also has this data. So it cannot on its own go and update it. It needs to take extra steps to write to this block. We are going to look at it as we go, right? So we, from the invalid state, we have seen processor write and processor read. Accordingly, we are taking step of processor read exclusive or processor read simple. Now, let's say we are in the modified state. The block is in the modified state. It means that I and I alone have the latest copy of the data, right? Imagine the very first example we saw. The P3 has updated the value of U to 7, right? And the value of 7 is only available with the in the private cache of P3. It's something like this. So P3 would have this particular block in modified state. Now, in the modified state, as long as the same processor is requesting for either read or write, we'll continue to supply the data. Means that particular controller will keep on giving the data to the processor or updating the value because it has the exclusive rights anyways. It need not put anything explicitly on the bus. Okay, but if it has if some particular block is in the modified state and the cache controller has seen that there was a read request for this block using bus read, so what it needs to do, it needs to put the latest, the updated value, whatever it has, right, onto the bus, and it will change the status of the block from the modified to the sharer because some other processor is actually asking. So at least 2 processors have this block. So we are making both of them in shared state. Okay, so that is the action item it would do, meaning flush, meaning it will place the data onto the bus, updated data onto the bus, and move on to the shared state. Okay, now so let me link it with the very first example that we saw. P3 has updated the value of U to 7. Now, after that, P2 has requested the data. Now, P2 would be having the block in invalid state, meaning that it was not there to begin with. It will be in invalid and it will go to the shared state, right, and place a bus read request. Now, this bus read will go to P3's cache controller and it will say, I have the block, here is the updated value, and it will move its own local copy from modified state to shared state. I hope you got the cause and action here, right? And let's say the current block is in modified state and it bus read exclusive was placed. The same thing will be done again. Let's say instead of asking for a simple read request, the P2 has asked for a write request. So again, it's a cache mess. So the P2's cache controller would place a bus read exclusive on the bus, right? This will be captured by P3 saying that, okay, there is an exclusive request. So I will forgo my ownership. I'll move my block from modified state to invalid state. And because I have the latest copy, I'll place the latest copy on the bus. Okay, so the block in P3 will move from the modified to invalid state, and the block in P2 will move from invalid state to modified state. Okay, this is how it would be interacting. Now, let's bring in P1. P1 was also having a copy of this block, right? So initially, let's say it has asked for only read permission, so it started off invalid and ended up in shared block, right? And as and when it sees that somebody has placed a request for exclusive rights of this block, it will move from shared to invalid. Okay, and as long as it sees that its own processor is requesting for read it will continue to supply the data and does not do anything. And even if some other processor is requesting for this data, meaning only for reading the data, bus read will be there, it will not react. So this way, the cache controller for each block, it will know which precise state we are currently in, and it will know what to do when a request from the processor has arrived, meaning it will either place bus read or bus read X, right? And it will also keep snooping the bus, and whenever a bus read or bus read X is seen by it, and it will go and see that, okay, I have the cache block, it will react accordingly. So this is our simple 3-state coherency protocol. So I again pause for a couple of minutes here. Please shoot any questions you have. So Dr. Lakshmi has a question on about the book. I have included the reference in the last slide. So it is Parallel Computer Architecture, book by Kuller, right? Morgan Kaufman are the publishers. So yeah, I'll share the slides anyways, you will get to know. Okay, any questions with respect to this protocol? Okay, let's go ahead, make things more complex as we usually do. Now, from simple M modified, shared, and invalid, now we are going to add one more state to it, which is exclusive. Okay. Now, why did we move from a simple 3-stage protocol to 4-stage protocol? Is even though we are having a multi-core processor, many times we might be running as single-threaded application. Now, what is happening is, even though I'm running a single-threaded application, only I am using the data because the data is not shared among others. Whenever I want to read or write, right, I will be placing a bus read or bus read X. And the other cache controllers are potentially not doing anything because they will always see a miss and they will remain in their states as is. But there is a lot of traffic on the bus. To avoid that, we have introduced another state, which is exclusive, right? So here, the block is clean, meaning that the processor will not have any permission to write to it, but it will also know that it alone has a copy of this block. No other process have the copy of this block. Okay. So with introduction of this state, the protocol will have obviously more transitions. But again, the point to note is this is invalidation-based protocol, meaning that we are going with write back caches. Also, by looking at the transitions, because on a processor write, we have placed a bus read exclusive request, meaning that we are going with write allocate policy. I hope there is no confusion there. Right now, again, if we quickly walk through what is happening from an invalid state, I can go to the shared state if I have request from the processor saying that it needs read. So I'll put a new request, a new type of command on the bus saying that bus read in shared mode. Okay, that is S. Or it can potentially, the processor can say that I alone need the block, right? And so it will do a bus read and it is put as shared with cap on it, potentially saying that it needs for its own rights and only for read. Okay, so it will move from invalid to the exclusive state. Now what is happening here is I have the block in exclusive state, and though I brought it for initially, a read with read requests only, now I decided to write to it. So what will I do? Whenever the processor has requested for a write, the cache controller simply moves this block from exclusive to modified. There is no action on the bus. So this is the saving we are getting from moving from MSI to MESI. Right, and rest all are more or less following the same pattern, right? So in the shade, if we are in a shade state, as long as the processor has requested for read, we will not do anything. But if there is a request for bus read by some other cache controller, we are going to put our data onto the bus, right? So so the flush apostrophe is given, saying that here, if you see, the cache is updating and is placing the value on the bus and supplying the data to the other cache. So the cache to cache transfers are allowed. If that is not allowed, what would potentially happen is the cache which has the block in modified state will update the memory first, and memory's duty, it's memory's duty to update the requester who has later on requested for the same block, right? So if cache to cache transfer is not allowed, then simple flush would be there. Okay, now from the shared status, again, if I want a processor write, just like earlier, we would place a bus read exclusive so that other guys can move their states accordingly. Now, so if you observe this state diagram, right, it is beautifully arranged that all the transactions on the right side are initiated by the processor. On the transactions on the left side are initiated by the bus, and the cache controller is reacting based on the state the block is in. Okay. Again, I'll pause for a minute. Please let me know if you have any questions. Okay, moving on. So what we have seen earlier are invalidation based protocols, meaning that we were using write back caches. Now we are going to look at a simple update based protocol, meaning we are going with write through caches, right? And with write through, which one is preferred, write allocate or write no allocate from our basics? Any answers? With write through caches, what would we be preferring? Write allocate, write no allocate? Even by looking at this state transition diagram, you can figure out. Okay, Ulas is saying that we would go for write no allocate. Okay, let's see if that's the case, right? So so here the four states are exclusive, shared clean, shared modified, and modified. Now shared modified meaning the block is out of sync with some other copy, but it has been modified. And shared clean is there are multiple copies, updated copies of the block, right? So again, here we have all the actions primarily driven by the processor only, right? So let's say we are in the modified state, and we are getting read and write requests from the processor. We'll continue to supply data. It will not, there is no specific action item on the bus. Now, if we have seen a bus read request, because the data is modified at our private cache, we flush it and we move to shared modified, meaning that somebody else also has it in modified state. Right now, if we look at okay, anyways, we are in shared modified state. As long as we are getting read requests from the processor, will not do anything. If the processor write has come, it means that because we are in shared modified state, somebody else also has the this block. Now, if I am updating my copy, it is my duty to update, to intimate others also to update their copies. So I will place a bus update on the bus, right? And if it has seen a bus read, right, it can potentially say that, okay, we are already in shared modified state. Now a new candidate is also requesting for the same block, right? So it will put the updated data into the bus. Now, if it is bus read, now if it is a bus update, right? So what it would do is from shared modified to, it will go to the shared clean, right? Meaning that it will update its own local copy with the new value. And as long as the processor read is continuing, it will continue. And as long as it will keep getting updates for this particular block, it will keep updating, right? And if it is a processor read miss, right, it will place a bus read shared request, and when the data comes, it will be placed in shared clean. And if it is a processor write miss, then we are going to have it in shared modified state, right? So on and so forth. If it is a processor read miss and processor read, and if we are in exclusive state, we'll continue to be in that. So you can walk through these individual arrows one by one to completely understand the protocol, right? Either we go for invalidation based or update based. The summary is we have some trigger points either from the processor or the bus, and the cache controller needs to act accordingly, right? So with that, I will conclude this part of coherency, and also in the interest of time, I'll pause here. The consistency part will be handled by another speaker in tomorrow, right, Dr. Praveen?
Hey,
Yes.
Devi Prasanna, Dr. Devi Prasanna Sahu.
Yes. So Dr. Devi Prasanna Sahu will pick up from where we left, right? And he'll speak about the consistency part. Yeah. So here are the references that I would suggest you to go through. Primarily, I have picked material from Parallel Computer Architecture book. As the title is Parallel Computer Architecture: A Software Hardware Approach by David Kuller. It is published by Morgan Kaufman, right? And there are a couple of other very good books which have the updated policies and decisions. We have stopped at MESI, but there are more complex policies, more efficient policies, right? MOESI, etc. And there are some tailor-made policies for that are followed by AMD and Intel by their own. Of course, we might not know all the details, but these books are updated, right? Okay, with that, I will pause today's session. If you have any questions, we can discuss. I'll share the slides on the same
Google Drive.
and you can access them via the same Google Sheet. Yes?
No, Google Drive.
Yes.
Yeah. Okay, Dr. Kalyan, thank you very much. Thanks for spending your valuable time for this lecture. Thanks a lot.
Okay, thank you. Thank you all.